If we look at today's big issues, we unfortunately must conclude that mankind fails to come up with proper solutions. Think particularly at the issues of climate change and energy transition. One of the causes of this failure is that the mainstream science in these areas is not fit for purpose. For sure, we need to carry on with further improvements in the many specialized scientific disciplines. However, using my over 60 years of experience in scientific research, I have concluded that big progress could be made by bringing together the knowledge from all these specialized disciplines. Not only from within one scientific area, but also by crossing scientific areas. This conclusion should not be a surprise, because the world around us is complex, meaning that thousands of different subsystems are interconnected with each other. This means that the real world functions as one massive integrated system, and scientific research should be organized accordingly. After I retired as director from the Geophysical Delphi Consortium in 2016, I continued my research on the Earth's climate system. As an experienced scientist, I was astonished to see that the mainstream climate models were not properly describing the real world, but were instead promoting a political narrative. In early 2019, I co-founded the Clintel Foundation with science writer Marcel Krok. In the past 6 years, Clintel truthfully informed people about climate science and climate policies from a science-based perspective that most people had not heard before. Clintel's World Climate Declaration, summarizing the key points of this perspective, has now been signed by almost 2,000 scientists, engineers, and economists worldwide. In my talk, I will show you how we can fruitfully combine the geophysical knowledge describing the world below the Earth's surface with the climate knowledge describing the world above the Earth's surface. In the diagram shown, here it is summarized that at the Earth's surface, the solar-driven natural processes in the Earth's atmosphere meet the tectonic-driven natural processes in the Earth's lithosphere. Together, they determine the living conditions at the Earth's surface. Today's mainstream climate science is in deep crisis. It is too much about models and too little about data. Even worse, the mainstream climate community looks through a narrow keyhole at the climate system. As a result, current climate models are too simplistic. The discussion is too one-dimensional, and the driving force is too political. Keep in mind that politicians love theoretical models. With these models, they can easily abuse science by steering the model outcome to what they have in mind. No surprise that their models predict apocalyptic warming in the future. Consequences are the net zero climate policies and the green energy projects. If these policies and projects continue, they will bring the Western world into bankruptcy. China and Russia love it. We know that in the situation of very complex systems, such as the Earth's 4D geological system and the Earth for the climate system, research should be largely data-driven. Not theoretical models, but real measurements tell the full story. Not looking through a keyhole at the present, but include massive historical data. Bear in mind that historical climate data from millions of years back can be found in the Geological Archive. From the picture just visualized, you see that the Earth's climate consists of many warm and cold periods. As can be seen, today's CO2 level has reached an historical low. Note that below 150 ppm, most life on Earth cannot survive. My message to you is that the rich scientific knowledge and the no-nonsense approach of geophysicists may provide a major contribution to solve the current crisis in mainstream climate science. Bear in mind, a physics and economics-based energy transition policy is indispensable to retain a prosperous Western world. As you know, imaging is the transformation of measurements into a 3D picture of the system under investigation. By repeating imaging at different moments of time, a 4D picture is obtained. As you are very well know, 4D geophysical imaging is a very powerful, non-invasive method to obtain information of the Earth's lithosphere in space and time. In the following, I will review with you the fundamental properties of climate modeling and climate imaging in terms of what is daily practice in exploration geophysics. In modeling, we start with a set of coupled theoretical relationships, and we generate pseudo-measurements by discretizing and solving the involved coupled differential equations. So, with modeling, we try to reconstruct with theoretical relationships what we observe in the real world. For complex systems, such as the Earth's climate, modeling is a huge scientific challenge. In climate modeling, the incoming solar radiation is numerically downward propagated through the atmosphere towards the spherical Earth surfaces. The result of this numerical radiation process shows how the Earth's surface is illuminated by the sun. Note that during propagation, both reflection and absorption take place due to the presence of aerosols and clouds in the atmosphere. Given the heat capacity properties of the Earth's surface, absorption of the net incoming solar energy leads to a warmer surface. Next, each grid point of the warmed surface acts as an infrared source. The infrared energy of all these secondary sources is numerically upward propagated through the atmosphere back into space. Now, this upgoing net infrared radiation leads to a cooler Earth's surface. Again, during upward propagation, both reflection and absorption may occur due to the presence of aerosols and clouds. In upward infrared propagation, however, absorption also occurs by greenhouse gases, such as carbon dioxide and water vapor. Bear in mind that this is the radiation story only. At the same time, Considerable heat transfer by thermal convection may occur as well. In addition, phase changes of the water molecule may take place from ice to water to vapor and vice versa, having a cooling and warming effect respectively. Note that all these physical processes are interconnected. In summary, I hope I have made clear that the 4D climate modeling process is a formidable scientific challenge. Claiming the science is settled is a political fiction that scientifically does not make any sense. Why do universities keep quiet? The climate is doomed narrative also explains why influential climate activists like Antonio Guterres, Al Gore, John Kerry, and also teenager Greta Thunberg have made bold, headline-grabbing predictions of the disasters that never materialized. There exists an embarrassingly long list of deadlines that have come and gone without the promised catastrophes. Given a specific choice of hypotheses and algorithms, the complex simulation process is followed by a validation process. In validation, the model parameters are optimized such that the difference between the simulated measurements and the real measurements are minimum, often referred to as a residue. Of course, the optimized model parameters must have a physical meaning, and the residue must be small. In climate modeling, this is not the case at all. No surprise that in climate modeling, both simulation and validation are far from settled processes. Particularly in the situation of complex systems, experience shows that it is better for policymakers to rely on rich images than on poor models. This message is the next part of my talk. Imaging is the counterpart of modeling. In imaging, we don't start with theoretical relationships and simulate measurements in the computer, but we start with acquiring real measurements, often referred to as remote sensing, and use the computer to transform those measurements into a structured picture. This means that in climate imaging we do not simulate, but we measure quantities, such as heat transfer. More specific, if we measure the upgoing infrared radiating field by weather balloons and satellites, temperatures at the Earth's surface can be estimated. In addition, if we also measure the downgoing solar radiating field by weather balloons and satellites, imaging provides an estimate of the heat capacity of the Earth's surface. No doubt you already have noticed the similarity between climate imaging and seismic imaging. For instance, natural illumination of the Earth's surface by the sun plays the same role as anthropogenic illumination of top reservoir by seismic sources. In both situations, the response is represented by an upgoing wave field. And this upgoing wave field obtains information about the target. Note that balloon measurements above the Earth's surface play the same functional role as VSP measurements below the Earth's surface. Obviously, in climate imaging, we demand high-quality measurement instruments. Imaging scientists should be prime customers of instrument developers. Think of the spectacular developments in microscopes and telescopes, such as the recent James Webb Space Telescope for finding the first galaxies that were formed in the early universe. But think also of the Delphi Consortium, where in the Delphi Acquisition Project, the needs in the Delphi Imaging Project were addressed. One interesting outcome was the blended acquisition concept, also referred to as simultaneous sources. In the diagram just shown here, you see that climate imaging also involves iterative processes in two coupled cycles. The imaging process begins with selecting the measured up and down going radiating wave fields. The next step is to construct from these radiating wave fields temperature images in space and time. These 4D images reveal the behavior of the climate system at the Earth's surface. In the characterization cycle, the images are searched for properties such as patterns, attributes, and empirical relationships. In the picture just shown, you see an example of the climate images we construct. It represents the atmospheric temperatures just below the oceans and continents. Note that the east-west average trends, the curves left and right, show a significant decrease if we move from the equator to the poles. This change has nothing to do with CO2. Most interesting is also that it can be accurately described by a feedback process with large negative feedback factors. Note that the doom discussions on climate warming are primarily based on a time function only, meaning that the complex 4D image is simplified to a simple 1D picture. In addition, the simplistic 1D picture is explained by the simple single factor CO2. Why do academies of sciences agree with this conclusion? When we compare climate modeling and climate imaging, it is important to realize that a model only contains the knowledge we already know. In contrast, measurements may contain lots of knowledge we don't know. In other words, in modeling, we apply existing knowledge, but in imaging, we are searching for new knowledge. In complex situations, truthful scientists are aware that what they don't know may be a lot more than what they do know. Therefore, in complex situations, truthful scientists are modest and would never, I repeat, would never make sweeping statements such as the science is settled. In the years that are still given to me, I will do my utmost to bridge the gap between the science in the natural processes above the Earth's surface, driven by the piping hot sun, and the natural processes below the Earth's surface, driven by the piping hot mantle. In this endeavor, imaging is the key technology. I hope I have made you aware that if we combine the knowledge and the experience in the climate and the geophysical communities and keep politicians far away from our scientific work, we can make a big contribution to humanity. I hope many of you will join me on this inspiring journey.